Complex engineering problem. Subject: power electronic. Topic: design a cycloconverter system for a rotary keel speed control in cement industries, focusing on torque stability. This PPT presented by Ketawat Suresh. Roll number 23951A0224. Department: Electrical and Electronic Engineering, 5th semester, A section. Content of the presentation: problem statement, objective, overview, requirement, prerequisites, solution to the problem statement, result analysis and conclusions. Problem statement: a rotary keel in a cement plants require the precious low speed operation with high torque. Traditional drives can produce torque, ripple, poor low speed torque, and instability under the varying thermal and load conditions. Design a three-phase cycloconverter based drive and control the system that provides the smooth, stable torque and accurate low speed control for a rotary keel, minimizing the torque ripple and ensure the reliable operation under the transient loads. Objectives: provide stable, continuous low speed operation down to few RPM for large rotary keel. Minimize the torque ripple and oscillations during steady state and transient events. Maintain the accurate speed regulation with fast disturbance rejections. Ensure the high power quality, acceptable THD, reactive power and management. Provides the protective features and diagnostics and the maintainability for the industrial users. Overview: a cycloconverter directly converts to fixed frequency AC to a lower frequency AC without a DC links, making it suitable for a very low speed and high frequency applications. For a rotary keel drives, uses a three-phase to three-phase cycloconverter, phases controlled or matrix types. Field cycloconverter or slip ring induction motors, common for very large keels. Implement a cascade control architectures after the speed loop, inner the torque current loop, firing angle, current modulation for a cycloconverter. Requirement: electrical power rating, matching the keel motor, typically several megawatts. Input: 3-phase 50 or 60 Hz industrial supply. Output: variable low frequency with controllable amplitude and phases. Converter topology: 3-phase cycloconverter, bidirectional phase controlled thyristors of matrix, cycloconverted with IGBT and IGCTs. Filters: LCL2 tunnel filters to limit harmonics, separation of cruciating current. Control and sensing: speed sensor, shaft encoder, resolvers, shaft mounted encoder. Torque measurements: dial the torque sensor, shaft torque sensor or high fidelity Torque estimator found motor current and voltages. Current sensor for phase high bandwidth CT or Hall sensor. DSP or FPGA based relay more time control with deterministic timing and 100 microsecond loop for inner loops. Prerequisites: motor data and keel mechanical inertia, friction and damping estimates, load the torque versus speed profiles. Electrical electrical supply parameters: short circuit level, nominal voltage, knowledge for power electronics, thyristor, IGBT, behavior control system and motor modeling, simulation tools, MATLAB, Simulink, if SCAD and test requirement, power analysis of scopes, data longer. Solution to the problem statement. Select the converter topology. Phase control the cycloconverter with the anti-parallel thyristors group for phase advantages. Proven for heavy industrial drive robots. Straightforward disadvantages: harmonic content, lower switches frequency limits, fine control. Matrix cyclo converter, if faster switching and better waveform control are requirement offer improve the torque ripple performance at higher complexity cost. Motor choice and interfaces: prefer the slip ring induction motor or synchronous motor sized for keel torque. For induction motor, used to rotary resistance controls or field control to shape torque characteristics. Third point, control the architecture. Output loop, set point, speed error to PI controller to torque. Common middle loop, torque command, current reference using motor model. Current output controller, inner loop. For phase controlled computing firing angle alpha to generate the output phase and amplitude, include the phase overlap management and commutation logic and avoid the circulating current. For matrix pulse width modulation, space vector like modulation to result analysis. Key performance of matrix: speed regulations, torque ripple, rated torque, response of time, speed loop settling within required time, THD at motor terminal, keep within acceptable range, efficiency, converter plus motor losses minus minimized by topology selection and cooling, stability, margin, phase margin, gain margin, inner loop. Conclusion: a properly designed three-phase cycloconverter drive with layered control can provide the precious low speed high torque performance requirement by the rotary keel by emphasizing torque phase feedback, active torque ripple cancellations, robot commutation and careful filtering. The system can achieve high torque stability and acceptable power quantity. The choice Thank you.